Hello friends, I'm Nikita and you are watching Prepare for Gate. Moving with the content of electronic devices, energy band diagram, carrier transport, generation recombination, Poisson and continuity, P-N junction and other diodes, and the implantation process at last. In this lecture tutorial, we will discuss P-N junction, Zener Diode, LED Photo Diode Solar Cell. Moving with our first topic, that's P-N junction. P-N junction is formed after the combination of P-type and N-type semiconductor through thermal oxidation of photoconductivity. A region of P-N junction is formed due to charge, carrier, and electric field. The electric fields are formed indirectly from positive to negative. The width of the field is formed at the junction. In transition region of it, the electric field is the gradient of contact potential. At equilibrium, the drift and the diffusion current just balance, which gives us the equation that mobility upon diffusion coefficient is equals to 1 upon the concentration of minority carriers and a differentiation in that concentration. Now solving further, if we kept from Einstein relation that mu p upon dp is equals to q by kt dot, I think I have missed an e in here. Similarly here. Okay. This E will be equals to dV naught over dx, which is similar to 1 over concentration into differentiation of the concentration. If we integrate both the sides, we'll get V naught is kT by q natural log of Pp over Pn. That means hole in the P region over the electron in the P region. If acceptor Na are present on the P side and donor Nd is present on the N side, then V naught is equals to kT by q Na over Ni square over Nd. Kt by q is natural log of any Nd over Ni square. Pp slash Pn is e to the power qV naught by Kt, a total uncompensated charge on either side of the junction, is QAx P naught into Ne, QAx N naught into Nd. According to the Poisson equation, the gradient of electric field to the local space charge at any point dE over dx is q by epsilon p minus n plus nd minus ne. Integrating the potential difference at that point to the width of the transition, which we have got earlier, is V naught is half E into V, or half q epsilon n dx naught n into w. V naught is 1 by 2 q by epsilon n a n d over na plus nd into w square. Xp naught is actually xp naught and xn naught is the region of is the total length on P side and total length on N side of the depletion region, which combines to form the width. The charge over N region and P region, Q of N is minus of Q A x N naught into Nd, and Q plus is Q A x P naught Ne. The electric field across the region E is equals to minus Q by epsilon xn naught Nd minus q by epsilon is x p naught into Ne. Now look at our very interesting question. In this, there you can see there is an N plus N silicon device and is fabricated with uniform and non-degenerate doping. We have talked that degenerate doping is an intrinsic type semiconductor, and non-degenerate means that it have an added impurity with Nd1 and Nd2. corresponding to the N plus, that will have more number of electrons as compared to N region. At the operational temperature T, assume complete impurity ionization, and KT by Q, an intrinsic carrier concentration is given. What is the magnitude of the built-in potential? We have known that V0 depends on both the concentration, then the magnitude will be dependent on its concentrations. Just donor concentration in one over donor concentration in another. The built-in potential is V0 of 1 KT by Q natural log of NT1 over ND. It gave me 1.73 volts. The forward bias P-N junction. If V volts is applied across the P-N junction with the P side connected with the positive side connected to the P side and negative side connected to the N side, under forward bias condition, the voltage across the P-N junction decreases as the potential gradient across the junction is in opposite direction to the applied field. The diode current I0 is equals to e to the power QV/KT minus 1. I0 is QA dP upon LP Tn plus Dn over Ln into Np. For low-level injection, minority carrier injections are considered. Under forward bias condition, excess charge carrier photon electrons in P type and excess charge carrier holes in N region. Distribution of excess charge carrier in P region and N region is the current due to the excess hole across XN region is IPXN is equals to minus QA dP differentiation of the whole distribution function will give me this value QA dP 1 over LP del PXN, which is QA dP over LP Pn e to the power QV/KT, where V is the forward bias voltage minus 1 e to the power minus XN/LP. This will give me the current across of hole due to XN. At Xn equals to 0, IP0 is QA dP over LP Pn e to the power QV/KT minus 1. Now here you can look at this diagram. I want to tell you that if this is an dopant where P region is heavily doped in comparison to the N region, thus the depletion layer is extended more in P region. Oh, I'm sorry. It must be the opposite, that P region is lightly doped and N region is heavily doped. So the depletion region is less in N region as compared to P region. And where the electrons and holes cross each other, they're the majority carrier in the region, but when they come to the edge, they becomes minority carrier. And with an exponential decrease, they decrease for a diffusion length having a constant time period. Okay, with Pn plus del Pn. Del Pn is a minimum value to which they decrease. Similarly, if we calculate for Xpn equals to 0, that is at the edge the concentration of electrons, or firstly the current, that is minus QADN over Ln Np e to the power QV/KT minus 1. Now the total diode current will be, if we add both the value, that will combine to give us QADP/LP Pn plus DNLN into Np e to the power QV/KT minus 1. I0 is this equation. If we put diffusion constant coefficient with the diffusion length, then the formula will be equals to diffusion length divided by the time period. and will give me this value of I0. If we look for a reverse bias junction, then if VR is the voltage applied across the P-N junction, positive side of the battery connected to the inside and the negative side connected to the P side, under reverse bias condition, the depletion region increases, and also the potential difference will become V0 the plus VR. V0 is the initial potential value plus the differential plus the applied potential. If I is equals to QA TP slash LP PN plus DN slash LN into NP, which is e to the power minus QV R slash KD minus 1. The total reverse current is equals to minus I0. If we look for XP0 and XN0, then the diffusion current at the edge of the transition region will be del NP and del PN. IN is equals to XP at 0 will be QATN, excess hole distribution differentiation over the length. For XP equals to 0, it will be minus QATN over LN into del NP. Del NP is the concentration of minority carrier with respect to time. IPN is minus of QATP del into del T over del XL. If we look for the charge in distribution divided by the minority carrier lifetime by the charge control approximation, we get this value that IN is negative and IP is positive. QALP upon tau P into del PN. This will give. We have only replaced the dP over LP by LP over tau N. Moving forward, if we divide both if we add both the equation, we get the final diode current, the whole current in N region, and the majority carrier current in N region will be QA dP over LP PN1 minus e to the power minus xn by LP plus dN over Ln into NP e to the power QV slash KT by 1. If we look for the GATE 2014 question, the doping concentration on P side and N side of the silicon diode are 1 into 10 to the power 16 and 1 into 10 to the power 17. Across P diode it is Ne, and across N side it is Nd. Forward bias voltage is applied, and at temperature T the intrinsic concentration and KT by Q values are given. The electron concentration at the edge of P side will be equals to the forward bias is given, carrier concentration except Ni is given, then P is Ni square over Ne at 0.3 volts. We get this concentration. P is equals to P e to the power V slash Vt. Under reverse bias breakdown, we got the Zener diode and avalanche breakdown. At reverse bias voltage, large current flow through the device with small change in voltage. The Zener breakdown voltage, which occurs few volts of heavily doped junction tunneling of electrons from P side to N side because of narrow depletion region, have electrons in many state of P region to many empty state in N region. Avalanche breakdown, which occurs at higher voltage in reverse breakdown region. For the AC, if we wish to calculate the stored charge at a function of time, then QPT is tau P into I e to the power T by tau P. In quasi-static approximation, Vt is KT by Q natural log I tau P over QALP Pn e to the power minus T by tau P plus 1. Reverse recovery transient. A reverse current larger than saturation current can flow in the junction during the time required for readjustment of the stored charge. the reverse current is minus E by R. If we wish to calculate the time delay, then time delay is tau p. Tau p is the Carrier lifetime of a proton, natural log of 1 plus IF over IR. The capacitance of P-N junction will be equals to dQ over dV. There are two types of capacitance: junction capacitance at the transition region and stored capacitance at the edge in reverse bias condition. The junction capacitance is predominant in reverse bias and stored charge is dominant under the junction is forward bias. At equilibrium W, we know that V0 is 1 by 2 Q by epsilon NA over NA plus ND into W square. Okay, and if there is a positive voltage, then we subtract that voltage from the potential, contact potential. At P plus N junction, where Cg is equals to junction capacitance is A by 2 under root 2 Q epsilon slash V0 minus V into ND. Now this is an important formula. It is often asked in examination to calculate junction capacitance or the transition capacitance or a capacitance in forward reverse bias condition. Then junction capacitance is A by 2 2Q epsilon over V0 minus V into ND whole under root. The storage capacitance is CS is dQ over dV 1 by 3Q square by KT A into Pn e to the power QV slash KT. Conductance by allowing small charges in the current GS is Di over dV. If the P-N junction is abrupt, the capacitance varies as the square root of the reverse bias. If it is linearly graded, then N value is 1 by 3, and if it is diffuse, then its value is 1 over 2.5. Remember these values as it often can be asked rather than an abrupt P-N junction or step-graded P-N junction. They can ask a linear P-N junction. Carefully read the question. That's the key, one of the key things to remember. Read the question properly in gate examination. So moving forward, we get the junction capacitance is directly proportional to VR to the power minus L. If we look at one of the question in 2050 on junction capacitance itself, where different biasing is being done across the capacitance, with the formula we can derive that the junction capacitance is directly inversely proportional to under root of V0 plus VR. If we put both the values, then we get Cg2 is equals to 2.5 picofarad. That's not a tough question. You just need to put the exact formula and try and get your answer. The metal function junction. It's often seen that when rather than two semiconductor forming a junction, a metal and a semiconductor can also form a junction. When a metal works with work function Q phi m and is brought in contact with a semiconductor having work function Q phi f, the charge equilibrium transfer until the Fermi level align with the equilibrium. For N-type semiconductor, the work function of metal is greater than the work function of semiconductor. For P-type, the work function of metal is less than the work function of semiconductor. And if we subtract both the values, we got the potential difference across the junction diode. If we look at photodiode, the carrier generated within the depletion region WR generates separated by the junction field, electrons being collected in the N region and holes in the P region. Also, the minority carrier generated thermally within the diffusion length on each side of the diffusion to the depletion region are swept to the other side of the electric field if the junction is uniformly illuminated by the photons with energy greater than the band gap and added generation rate GO at a added generation rate. Then the number of holes created per second within the diffusion length of the transition region on the N side is A into diffusion length of holes into the rate of generation. Number of electrons created per second within the diffusion length of the transition region on the P side. Then it is area into diffusion or diffusion length into rate combination. The number of holes and electrons created per second within the width of the transition region on the P side is given by this formula. The total optically generated current will be I optically will be Q A diffusion length across P region plus diffusion length across N region plus the total diffusion length will give me the current generated through optical activity. The total diode current then can be found by getting the total diode current minus the generated current. Now I will look for the value to calculate VOC, an open circuit voltage having different optical generated current and diode current. That will give me KT by Q, natural log of LP plus LN plus W slash LP upon tau P into PN plus LN into tau N into NP into GOP plus 1. If we calculate the thermal generation, then and GOP in optical generation, then VOC is KT by Q natural log of GOP slash G. Now in fourth quadrant, the junction voltage is positive and the current is negative. In such case, power is delivered from the junction to the external circuit. Now let's look at one of the question. Oh, before that we should know what is solar cell. Now solar cell is the cell we have been talking about most recently, which converts the solar energy into electrical energy. For that we need to know 4 parameters, which is short circuit current into open circuit voltage into maximum IM voltage, maximum IM current and VM voltage. Now here it should be written as current. Now to know the fill factor, we have VM over IM slash VOC over ISC, maximum power to the load will be fill factor into VOC over ISC. This was a question which have appeared in GATE 2016. It is shown that ISC and VOC are given. If both are given, having an input voltage, we can calculate that. Okay, moving on. The last is light emitting diode. In a material characterized by direct recombination or the direct band gap semiconductor, light may be given off from the junction under the forward wires. This is called the junction electroluminescence. For LEDs, the frequency of photon is governed by the band gap of semiconductor as given by the Planck's relation, which is 1.24 by lambda. At last, I would like to say that electronic devices comes with the paragraphs type question, but they are comparatively easier to solve. So test yourself by solving more and more such type of questions. Bye bye. Thank you very much. If you like the video, kindly press the like button. Subscribe to my channel for more videos related to GATE examination. Thank you. Bye.